Today we're talking about Chapter 2, Section 3, the derivatives of natural logarithmic functions. So the previous section, we took the derivative of e to the x, which we know is simply e to the x. This time it's not as easy, but it's still pretty simple. Once you know how to do it, right? So I was told that I don't have to be as rigorous with the proofs in this course, but I will still snip how we derive the natural logarithm. So this is our derivative of the natural logarithm, but I'm going to go ahead and do you one better because this is just one of those instances where I feel like you're told half the story, and then you're told the other half after you do something first. So we're gonna first look at Theorem 8. I wonder if I can put that. Let's put on a new page real quick, and then we'll put it right beside Theorem 7 here. Alrighty, so that's a lot of snipping there. So in order to derive the natural log, rather the derivative of the natural log, all right, let us assume that we're trying to find the derivative of some f of x, where that some function, and that function is the natural log of x. Well, we can rewrite the equation by raising both sides to the exponential equation. And so notice how we're just raising e to what the function is. We don't know what the function is, right? What we do, it's natural log of x, but we're raising e to a function, and then when we raise e to the natural log of x, remember that's just the argument, which is x. And then if you differentiate both sides, we recall from the previous section that the derivative of e to the f of x is just simply, or e to the x, or e to the anything, was just simply that exponential form times the derivative of what I'm being raised to, right? And if you do all that, you end up with 1 over x. This is the derivative of natural log of x, which is 1 over x. And that's what Theorem 7 is stating. But Theorem 8 is the one I want to really pay attention to because it's uh, it's more precise, and on top of that, it's for every number, right? Because in this particular case, well, in both the cases of deriving and Theorem 7, we simply have an x for an argument. All right, well, what if we had like a 3x, right? Or 3x squared? Well, that's what Theorem 8 is telling us. So Theorem 8, if we take the natural log of some function, then that's just going to be 1 over that function times the derivative, or more concisely, we would say the derivative of the argument over the function. Okay, and we'll see more examples of that here in a moment, but it's pretty easy when you just take the derivatives of natural logs. Okay, and what I circled there is what we're going to be doing um, for for an example. You're like, well, what do we do here? So that's going to be that. So I don't think we need this theorem right now. Uh, so starting off with example one, A seems to be pretty easy, right? This is just y is equal to 3, right here. Y is equal to 3 times the natural log of x. Well, we know that we can simply just kind of split that up into 3, and then again, the symbol here just basically means take the derivative of, right? So we're going to take the derivative of natural log of x. Well, we were just told that natural log of x is 1 over x, So we're going to have 3 times 1 over x, or in other words, 3 over x. Pretty easy. B looks like we're going to have to do our uh, product rule. So let's go ahead and do our product rule. And C is going to take the quotient rule. So I'm just going to go and put C on the next page. So I'm going to do the rest of this with B. So we have y is equal to x squared times the natural log of x plus 5x. So we're going to have to do first times the derivative of the second plus the second times the derivative of the first for just this first term here. Okay, so let's go ahead and do that. So first times the derivative of the second is going to be x squared times the derivative of the second, which is going to be 1 over x, plus the second, which is the natural log of x, plus second, times the derivative of the first, which is going to be 2x, right? And that's just the first term, right? So what I just kind of underlined there is the same thing as that. And then we're going to say, plus the derivative of 5x. Well, what is the derivative of 5x? Well, that's just going to be 5. So plus 5. And if we uh, put together some like terms, don't really have many. Well, we can't really put together too many like terms because in this particular case, we have, 3 terms to begin with, right? We are separated by the addition sign just 3 times. So in the first part, x squared times 1 over x, well, that just becomes x squared over x, which is going to be x. And then plus, we have the natural log of x times 2x, and then we can just write that as 2x natural log of x, and then plus 5. And then real quickly, because I'm afraid that I might have just hand waved through that a little too quickly. Recall that we've got that this can turn into x squared over x, and then that's where I just got the simple x on here from. Okay, and we'll do C now. Okay, so this tells me I already have to do low d high minus high d low, right? So we have C, and then we've got the y is equal to the natural log of the natural log of the absolute value of 2x over x cubed. We're just gonna have to do low d high minus high d low, right? That the derivative is just going to be that. So low d high, we've got x cubed, and then times the derivative of the top one. Well, this is where I wanted to really shine, and well, real quickly before we do get to that point, um, the natural I'm sorry, not that natural log, the absolute value might be throwing a little kink into this, but it's really not, because we see that if we just have the natural log of the absolute value of x, then it's just simply going to still be 1 over x. So nothing really changes with the absolute value symbol. But where did my theorem A go? Okay, here it is. All right, so this is kind of why I wanted to put the theorem 8 before we actually even did example 1, because what I was focusing on was this right there. Right, I said theorem 8. Theorem 8 follows from theorem 7, but I think we had natural log of we had the natural log of the absolute value of 2x. Okay, well, following along with what this is reading, then that says what I will do is I will put the derivative of my argument. In this particular case, it's simply a 2, right? The derivative of 2x is 2, right? Over the function, and the function just is simply 2x, so it's going to be 2 over 2x. Okay? And again, theorem 8, for some reason, is coming after example 1. I mean, it can be solved with just theorem 7, but I feel like having theorem 8 really helps. But the natural log of the absolute value I'm sorry, the derivative of the natural log of the absolute value of 2x is going to be 2 over 2x. So that's what we're going to put. So we're going to put 2 over 2x. All right, that's low d high. Now minus high d low. And then the high is obviously the natural log of the absolute value of 2x times, and then the derivative of the low is 3x squared. And that's all over low squared, which is x to the sixth. Okay. And then I'm going to clean this up, and let's zoom in on this real quickly. We know that the 2 over 2x, the 2's cancel, so we end up with a 1 over x, right? And that's to be multiplied by x cubed. Okay, we know this is the same thing as saying x cubed over x. Well, that 3 cancels and that x cancels, so we're just left with an x squared. Okay, so I'm just going to put the x squared in on the first term there. I guess I can just do back. So I've got x squared and then minus, and then we're just going to clean up this part here. We're going to put the 3x squared first, so we're going to say 3x squared. It looks like we can factor out an x squared, so maybe let's actually write that a little smaller because I'm going to be factoring some more. Okay. And then, as mentioned, it looks like I can factor out the x squared and then my numerator. And so I'm going to factor out the x squared. And that leaves me with a 1 minus 3 natural log of 2x all over x to the sixth. And then we can cancel the x squared and then cancel 2 of these to make that a 4. So let's see if I'm sure I have room. So we can make this a just simply 1 minus 3 natural log of the absolute value of 2x. Actually, I don't need a parentheses there. All over x to the fourth. Okay, so nothing changes. We still have our product rules and quotient rules that we learned at the beginning of this section. We still have to do that a lot, but the past 2 lectures we learned the derivative of e to the x, and now we're learning the derivative of the natural log of x. All right, but let's do another example that really drives the Theorem 8 point home. And you're going to love how we do b. b is pretty easy compared to what you think it's going to be. All right, so Theorem 8, again, let's go back. Let's go back and look at it just to really super duper drive this point home. I take the derivative of the argument and I just put it over our function. That's it. Okay? Or I'm sorry. I say out of the function. I take the derivative of the argument and just simply put it over the argument. Okay? So let's put that into practice. So what does that mean? Okay, so we're going to take the derivative of the natural log of x squared minus 5. Okay, well, first of all, let's just go ahead and ask ourselves, okay, so what is the derivative of x squared minus 5? Well, the derivative of x squared minus 5 is just simply 2x, right? Because 5 obviously does not have a derivative. So it's just going to be 2x. So I'm going to put a 2x in my numerator. And then in my denominator is just what the argument is. Well, it's x squared minus 5. And that's it. Well, we did it, right? We just take the derivative of the argument and put it over the argument. That's it. Pretty easy. Now b, like I said, it looks like it's going to be a doozy, but if we recall, our logarithm rules, okay, so if we recall our logarithm rules, then we know that we can actually rewrite this into something a lot more pleasing to the eyeballs. The natural log of x cubed plus 4 minus the natural log of x. And now that is so much easier. There's no Lodi high minus Heidi low. There's nothing. There's none of that stuff. Instead, all we're just going to do is we'll take this one at a time. We're going to work on this first term. Okay, well, what is the derivative of the argument? Well, that's just going to be a 3x squared, and we're going to put it over the argument, which is x cubed plus 4 minus, right, what is the derivative of x? Well, that's just 1 over the argument, which is x. And that's that. Super duper easy, right? All right, and we have one more example. There are four examples in this section, but the fourth one is not, it's not really much calculus involved. Plus, it's a lot of calculator work, and as I've mentioned before, calculator work on YouTube videos are just kind of silly looking. So we will do this one, but this one is also easy. When I was a student, I remembered we would do word problems, and I would just get a sense of dread, and especially on the test, I'm just like, well, I hope I get this right. I hope because I'm not going back and trying it again. But I don't know, I was just a very very lazy student, and obviously I grew out of that because now I'm teaching, right? But if you have that same mindset, just give it one read, and you're gonna be like, oh, okay, this is gonna be pretty easy. And let's proceed with that thought process, right? So, and this is pretty cool. This is the law of forgetting. It doesn't actually say that, but this is the law of forgetting. In a psychological experiment, students were shown a set of nonsense syllables such as POK, RIZ, DEQ, and so on, and asked to recall them every minute thereafter. The percentage R of T who retained the syllables after T minutes was found to be given by the logarithmic learning model. R of T is equal to 80 minus 27 natural log of T for for T between 1 and 15. So really quick, before I even unpack this, I think I might have said it before, but these equations right here aren't just pulled out of thin air. These equations are built from calculus, the other side of calculus, which we'll do called antiderivatives or integration, um, in a class called differential equations. Okay, so these equations aren't just pulled out of nowhere. Through numbers and data, you can build equations like this and all equations. Right? So that's number one. Number two, notice how we say that for t between 1 and 15. Okay, so all those times that we have discussed in well, not just this class. I can't remember if we have it in this class or not. But in your previous courses where you've talked about the domain, well, this is why domain matters. Okay, so for this particular example, we're limiting this only for t between 1 and 15. When it is less than 1 or greater than 15, then there's no solution because we are only worried about 1 to 15. That is the domain. So whenever we talked about domain in previous classes, it's very important that when you stick within the restricted domain. So anyways, A reads, and this is not even a calculus problem. This is just this is just a look at the chart problem. That's the same way example 4 is. So what percentage of students retained the syllables after 1 minute? Well, okay, so we're just gonna look here at 1 minute. Up here, looks like about 80%. So, huh, there's a brain buster. Here's your easy one for the day. B reads, find r prime of 2 and explain what it represents. Okay, so r prime of 2. What that means is we have to take the derivative of r, right? And r is just our function here. We're going to take the derivative of it. So let's go ahead and take the derivative of it first. Okay, so we're going to take the derivative of 80 minus 27 natural log of t. Okay, well the derivative of 80 is nothing, right? It's just 0. And then we have minus 27. And then what is the derivative of the natural log of t? Well, again, that's just going to be 1 over t. Or we can write this as negative 27 over t, right? And we want to find r prime of 2, so all we have to do is plug in a 2 for t. So r prime of 2 is equal to negative 27 over 2, which is a negative 13 and a half. Let's move it over to the left tad bit here. Which is negative 13.5. Okay, so r prime 2 is negative 13.5, but this also says, explain what it represents. All right, well, what this represents is that after 2 minutes, these students are forgetting at a pace of negative 13.5% per minute. Right? Their capacity to remember is declining at 13.5% basically. And C, let's see. Yeah, we're just going to put this on a new page. Okay, C again is not even a calculus problem. C is just simply a college algebra problem, but we'll do it. Okay, so C reads, when will the percentage of students who retain the syllables drop to 20%? Alrighty, so one way, and this is obviously not a good way at all because you don't necessarily know. It's kind of hard to tell, but just kind of ballpark. If we were to put this at 20, put us a horizontal line there, and it looks like we cross about right here. So about 9.5 minutes or so, right? But that's not a good answer. Instead, we have to do it, algebraically. So it reads, when will the percentage of students who retain the syllables drop to 20%? All right, well, let's go back and let's examine what our equation is, what our equation here is. Okay, we have the 80, which isn't anything, 27, which isn't anything, natural log, which isn't anything, but t is a variable there. All right, but t just represents time. Okay, so that takes care of the right side. There's nothing to do over here. The left side, what does the left side mean? Well, the left side, r of t, right? R of t can just be y or anything, right? It doesn't matter. But r of t is the percentage who retain the syllables. Okay, so it looks like what we need to do is we need to put 20 over here for r of t. Should we do 0.2? No. Yeah, so we just have to put a 20 over here for r of t. And that's it. And then we're going to solve for t. So our equation is going to look like this. It's going to say 20 is equal to 80 minus 20, let's fix that up, 27 natural log of t. And then let's do the arithmetic here. So we're going to go ahead and subtract 80 from both sides. So we've got a negative 60 is equal to a negative 27 natural log of t. All right, and then we can go ahead and divide both sides by a negative 27. And we can reduce that to what? Looks like 3 goes into about 20 over 9. So we can reduce that to a positive 20 because it's a negative divided by a negative. So 20 over, let's say 9, 18, 27, yeah. And that's equal to the natural log of t. And at this point, the way we solve this, of course, is we take, we raise both sides to e. Okay, so we'll have e, put this in blue now, put e to the 20 over 9, right, is equal to e to the natural log of t. But we learned in a previous section that e to the natural log of t is just t, right? It's just the argument. So we can just simply write t on the right side here. And then what is e to the 20 over 9? e raised to 20 divided by 9 is 9.23 is equal to t. Okay. And really quickly, before we do wrap up this section, I want to, I can't remember if I did it or not the other day, but whenever I put something into the calculator, uh, if I, and I did because, I knew I was going to go back and put parentheses in, but if I just simply put e and then a little caret on my calculator, 20 divided by 9, okay, that's what I want, right? But that answer gives me something like 53 million, which isn't anywhere close to the time frame there, right? But if I go back and obviously put my parentheses in, that's when I get 9.23. So once again, if I didn't do this, if I haven't done this semester rather, I just urge you to be very, very liberal with your parentheses whenever you put stuff into the calculator. The calculator, I dare say that, will always be right, but if you're incorrect, it's going to be, user error. And this is the summary of the section today, and that concludes today's lecture.